so the first video was about coarse versus fine grain, plutonic versus volcanic rock. So we use that texture, coarse versus fine grain, to interpret whether or not the rocks were plutonic, cooled underground, deep underground, or volcanic, cooled at the surface, erupted onto the surface. So that's an important part for interpretation. The next thing I'm going to introduce is some other textures. These are some of our more specific textures. Rather than just simply fine or coarse grain, we can get into some more nitty-gritty stuff. And the first one I'm going to introduce is porphyritic texture. Now, if you look, I'll have a photo of this rock, but this rock looks speckled. But you see very large crystals, and in between those very large crystals is a uniform color. From your perspective, it's pretty much a uniform dark gray. So that tells me that the background is fine grain. So that is what I interpret as. That means it is a volcanic rock. It cooled very quickly. But this magma was a slushy before it got to the surface. So these plagioclase crystals, these white ones, were crystallizing in the magma before it reached the surface. So inside the magma chamber, the crystals were happily crystallizing, and then something changed and the rest of it came up to the surface, began cooling, and crystallized very rapidly. So that is a common thing in certain kinds of volcanic rocks, especially the andesites. So let me get this one wet so you can see it a little bit better. But this one, there are some black hornblende crystals and then a uniform dark gray background. It's very common for andesites to have porphyritic texture. That's what that's called, porphyritic texture. And I think of it a bit like thinking about a chocolate chip cookie. So in a chocolate chip cookie, you've got the cookie. You can't really see any parts of the cookie. It's just a uniform tan or brown color. And then you've got chocolate chips in it. And those chips are much larger. In addition, those chips existed in the mix before it was a cookie. So think about that. When you mix the cookie dough up, you've got all this all the stuff that the liquid part, and then you've got these chunks in there, these chocolate chips, and they were solid before you put it in the oven to cook your cookies. So that's the same thing with porphyritic texture. Those crystals were in the magma as crystals, growing happily, doing their thing. Then the magma erupted, and the rest of it crystallized. So that's like putting it in the oven and then bringing it out, and there you go, you got your cookie. So this solidified at the surface then, and the larger crystals, in that one or like this one, those larger crystals stick out like chocolate chips in a otherwise fine-grained background, which is the volcanic equivalent, the fine-grained texture. So we can have porphyritic fine grain. We also can have porphyritic coarse grain. And right here, there is a very large potassium feldspar crystal. There's one, here's one, and way over there is one more very large potassium feldspar crystal. So these potassium feldspars were crystallizing in the magma before the rest of it did. Now this one didn't erupt to the surface because this is a plutonic rock. You can see it's speckled. You can see, I can see the white is plagioclase. There's some little gray bits of what look like glass. Those are quartz, and then all of the black specks are hornblende and biotite. So this was a liquid with chunks of potassium feldspar or K-spar in it. Something happened to change. Temperature became a little bit cooler, pressure a little bit less, whatever the conditions are that resulted in the rest of the rock, the rest of the magma crystallizing slowly, but at a pace that is more uniform and does not allow them to get too big. So we can have porphyritic coarse grain, and we can have porphyritic fine grain. So but usually with porphyritic texture, it doesn't matter so much in the coarse grain for identification, because you would still call this a coarse grain rock even though the potassium feldspar crystals are very large. If you only concerned yourself with this one and said, oh, I can see some crystals in there, it must be coarse grain, it must be plutonic, that would be wrong. So that's why it's really important to pay attention to whether it's porphyritic or not. That just means 2 stages of crystallization. There were crystals happily crystallizing in the liquid magma, and something happened, temperature change, pressure change, or it moved up into, higher into the crust, or erupted on the surface, and then the rest of the rock crystallized either slowly, like my granite here, or rapidly, like my andesites, basalt, and to an extent, maybe this rhyolite, but it's a little iffy on that one. I would question that. So that's porphyritic texture. The other textures we have are related to volcanic rocks, and they include, like this obsidian, and obsidian is volcanic glass. And sometimes you may see obsidian as totally black. That's very common. This happens to be what's called mahogany obsidian. It's just a fancy term for brown obsidian. And that brown is the result of other chemical constituents or some changes that occurred in the magma as it was crystallizing, or later on after it was buried. And one of the things that obsidian will do over time, even though it's glass, when it solidifies, because it solidifies so fast that no crystals grow, none, not a single crystal. You can think of it as if you made a cake for your friend for their birthday, and instead of baking the cake, you decided, well, I don't have time to bake it, and I gotta go, I'm just gonna put it in the freezer, and it'll be solid when my friend comes over, so that's a cake, right? I think we'd all agree that that's not a cake. That's just a bunch of mixed ingredients that froze. So this is like the cake batter in the freezer. There are no crystals in here. It is all glass, and glass has no crystals in it. It has all the ingredients to become crystals, to become minerals, but they never had the chance to grow and to organize themselves into that crystal structure that makes it makes all the molecules. And the molecules may even be in here, but they're not attached to anything. They're not in a crystal structure, so they're not minerals. The other thing that happens to obsidian over time is because glass is not stable on Earth, on the surface of the Earth. It's an I don't want to say unnatural way for the glass to be, but it's not a stable. It's not an equilibrium with the environment. So over time, it would actually crystallize to quartz and some other minerals over time. It's called devitrification, or going away from being glass. So this texture, when it's all obsidian and it's all volcanic glass, we call that a glassy texture because, well, it's glass. This is pumice, and pumice, you probably have some at home if you use it to scrub something. These are often made with scrub stones. If you scrub your feet, you can buy pumice to scrub calluses off of your feet or your hands. If you work with engines or engine oil, there's lava soap that has bits of, to grind away that oil and really get it off your hands. It'll often have bits of pumice in it. And pumice is, it's all of this that we see here is a froth of glass. So this is frothy volcanic glass, and we call it, and because of all of the holes that are in it, it's referred to as being vesicular because it has vesicles. So all these little holes, this holy rock, those holes are called vesicles. That makes the rock texture to be vesicular. This is actually, because it has so many holes, there's more air in here than there is rock, and this is a rock that'll float. In fact, this particular one has some minerals that grew on top because this was actually floating in a lake in California at some point in the past, and some of those minerals crystallized on top of it. So that's pumice. That's vesicular texture. We can also have one, this basalt here called vesicular basalt or scoria, has a lot of holes. This also has a vesicular texture, but unlike pumice, which is volcanic glass, this is actually composed of minerals, just like any other basalt. It just happens that the gas bubbles, as it was crystallizing, the rock formed around these little gas bubbles that were coming out of the magma. So we can have vesicular basalt. We can also have pumice, which is vesicular. And the last texture, volcanic texture we have that's not related to identifying if it's coarse or fine grain, like we did in the first video, are these tuffs. And tuffs are an interesting rock. The only thing that all tuffs have in common is that their background is, or the majority of the rock is volcanic ash. So that means that for either of these rocks, a volcano erupted, material was thrown out of the volcano. In fact, in this one, you can very easily see, and I'll have, if you look at the pictures, there are chunks of volcanic rock in here. There's all different kinds. There's also some pumice fragments, and these holes that are here, those were pumice fragments, but because pumice is so fragile, anytime that you have a rock left out in the environment, weathering away, those pumice fragments will break up very quickly over time. And of course, remember, we're talking geologic time, so very quickly might be 10,000 years. But compared to 500 million years, that's pretty quick. This one does not have many rock fragments like that one does, but it has pumice fragments, so I've got little squished pumice fragments, which, because this is so hot sometimes when it's deposited, when it rains down off out of the volcano, it can still have an awful lot of heat associated with it, and those pumice fragments can get a little bit squishy, and as the weight of the ash and all of the material kind of weighs down on it, they'll get a little bit flattened. So we can see some flattened pumice in this one. One of the things with a lot of tuffs, especially airfall tuffs as these are, so these aren't, there's another term called welded tuffs, and it's actually so hot that it just kind of gets all welded together and it becomes a really solid rock. But these are ashfall tuffs, so they're falling out of the air and eventually being formed into a rock after the ash has all deposited. So you think about like an eruption of Mount St. Helens, or Mount Vesuvius would have some. Also, any of the Mount Pinatubo, a lot of the volcanoes that have erupted in the past, does not include Hawaii though, and we'll cover that more in chapter 6, but some of the more, the volcanoes that are located along convergent boundaries, so we just did convergent boundaries that have the subduction, and where there's subduction, there's a volcanic island arc or a volcanic mountain range, and those volcanoes in the volcanic island arcs or the volcanic mountain ranges along a convergent zone will produce these tuffs. If they can be very violent eruption. They can be volcanoes that erupt very violently, and so they'll blow stuff into the air and they can produce tuffs. So that's our other types of textures. We've got porphyritic texture, which is what I call the chocolate chip texture, and that's common, actually most common in andesites. So that's why we cover it in physical, because so many of our andesite rocks are porphyritic, and if we never introduced it, you would say, oh, well, that's a coarse grained rock, when in fact it's not. It does happen in rhyolites, not as often. It does happen in basalts, not as often. Because it happens in andesites so frequently, it's flying overhead, we have to introduce it, otherwise it would be very confusing. Alright, so the next video that will be is about composition, mineral composition, and the partner rocks.